Hello, my name is Bradley Van Dam, and I will be doing exam chapter 31 and 32. Or specifically for questions 3.1 through 3.4. So let's get started. So for part A and B, we're given the following information: an inductor with, let's see here, inductance of 2.5 millihenries, part of a circuit, aviation radio beacon, operates 108 megahertz. It wants us to find the inductive reactance of the inductor. So, use the expression here. 2 pi times inductance times frequency. Looking for the inductive reactance. So, let's see. Yeah, so we have everything here, so we can just plug in. 2 pi times, so 2.5 times 10 to the negative third times mega, so that's, times 10 to the seventh. So, yeah, let's plug in the calculator. So, 2 pi times to the seventh gives us, let's see, 1, 2, 3, 5. See here, 6, 7. Okay. So that's 1.69 or 696. I'll say 1.7. Remember rounding that. Times 10 to the, what is that? 6th ohms. Okay. And then part B wants us to find the amplitude of the current in the inductor if the amplitude of the voltage across the inductor is 4.2 kilovolts. Okay. And that is VO. So we're now looking for IO. That's just going to be VO over XL. So we know, based off that, we know both of these now, using the XL from previous problem. Let's see here, 4.2 over yep. Gives us 1, 2, 3, 2.48 amps. It's 3.1. Okay, so 3.2. This is an AC circuit, includes a resistor with resistance. So I'll just say 3.2 given 25 ohms. Connecting the series the capacitor of C equals 7 microfarads. Current through the resistor and capacitor is given by the following expression. So that's I equals 2.4 times 10 to the negative third amps times cosine 1 1.75 times 10 to the third radians per second. That's multiplied by t. And it's the question says to find, or asks us to find the voltage across a resistor as a function of time. So we're given this. This represents the current through the resistor and the capacitor as lowercase I. So let's see. We're looking for the voltage across the resistor. So VR. Okay, yeah. So we can just do. So solving for VR. So circle that guy. Equals, and then we're essentially just going to have the expression I times resistance, so IR, and so then we just plug our things in, so equals this long expression, so negative third, yeah, negative third times cosine, and I'm just going to leave the variables out here, so 1.75 times 10 to the third. And let's see here, that's multiplied by 125. That should give us the solution here for that VR. So let's see, 2.4 cosine of times 125. So that is 2.9 repeating, so let's just say, let's round that to 0.3, and that would be, oh, sorry, yeah, so no, we're not gonna actually, I'm forgetting how the problem wants us to format it, so it's not gonna be all that, so we're gonna multiply the, since essentially this is, I forgot to include that, the t there, so this is still with t, so we leave this guy alone, but multiply 125 times, so get rid of the cosine. Ooh. Oh, nope. There we go. So we just want the 0.3, which is still going to be multiplied by the cosine since we don't have t yet. So we're going to have 0.3, and it's going to be 0.3 volts multiplied by cosine of the 17 or 1,750 or 1.75 times yada yada. So I'll just do cosine 75. That is, yes, that is the expression. That is C. Part D wants us to find the capacitive reactance of the capacitor. So we can solve that by XC equals 1 over omega times resistance. Oh, sorry, not resistance, sorry. Capacitance. Yada equals, let's see here. So that's, okay, so the omega is 1750. And then for our C, we're given that here. So that's 7 micro negative 6 all over 1. And yep. It gives us 81.6. And that is in units of ohms. Part E wants us to find the voltage across a capacitor as a function of time. So we're going to do VC, and then, yep, equals I times 1 over J omega times capacitance. Looking for this guy. And so using these two expressions here, we can rewrite this. So we can just do a little arrow, rewrite this expression. Since we already know that x of c is this expression, so we can say I times j times what we already know. And that is, again, this expression up here. So I'll leave, I'll just write it out. Why not? So -3 cosine 1750. I'll just say 1750 from now on, just to make it simple. And then t. Actually, well, you can get rid of that. 1750 times our j times 81.6, and it's going to equal, yeah, multiplying it together, 24. Yep, 0.9116. So J and then we can move the J inside, and then we have, so 0.196, and then cosine of that expression, and then minus the pi over 2 from the J. You're moving this into our cosines. Then we have cosine of 1750. And this is going to be minusing that pi over 2 value. That is for part E. Okay, going on to 3.3. So for parts F through I, so an AC circuit includes a 155 ohm resistor. So let's say R. Resistor in series with a 8 microfarad capacitor. 6 capacitor. Current in the circuit has amplitude 4 times 10 to the negative 30 amps. So we have equals amps. And it wants us to find the frequency for which the capacitive reactance equals the resistance. Okay. Oh, excuse me. So in this problem, let's see. How can we do this? We're looking for frequency. That's the end goal. So, okay, yeah, so when it equals the resistance, so we have the capacitive reactance, and then equals, when it equals the resistance, which also equals 1 over 2 pi times frequency times capacitance, and we're looking for frequency, so we can rewrite this expression here. So R equals this, and we could rewrite that where we take out the F, solving for F, again circling that as what we're looking for. And then R gets put in the denominator, so we get 1 over now 2 pi, essentially R is just taking F's place for frequency, so we're just replacing that, 2 pi RC. So now we just plug and chug. So we have 1 times 2 pi times 155 times capacitance given times 10 to the negative 6 Nope. And that gives us, can't round that up, so it's just 128, just to round to a whole number here for the frequency. 128 hertz. Part F. Part G, so it says, at this frequency, what are the amplitudes of the voltage across the resistor and capacitor? So we can make this assumption here. So we can say VC is also equal to VR. And again, we're solving for these two guys, so I'll just circle them. So these guys should be equal to one another, and then that's going to be equal to saying the same thing as times XC. And so we have, let's see. Let me think. Oh, okay. So we have the 4 amps, and then the 155, because we know that's the similar way to represent that. We can say X equals R, so 155. Let's multiply that out. Oop, third. 0.62, and that will be the solution for both C and R, or VC and VR. So, yeah, so that is going to be for part G, both these guys. So I'll put them in, I'll just put a comma between the two. 62 volts. Okay, and then part H, at this frequency, okay, so for both part H and I, it says, at this frequency, the voltage across the resistor is at maximum. What is the voltage across the capacitor? Yeah, so for both the VC and VR, both of those are going to equal 0 at the time, or when the resistor is at its maximum. It's going to be both 0 voltage for both part H and part I for VC and VR. Okay, so then that is 3.3. Let's go to 3.4. Running out of space here. Okay, so this one is parts J through M for the last question. So we are given a, resistance 116 ohms. A resistor and an unknown capacitor are connected in a series to an AC source with an angular frequency omega 5.10 times 10 to the third. Yes. Radians per second. The amplitude of resistor voltage is 2.45 volts. 2.45. And the current in the circuit has its maximum positive value at t equals 0. So at the very beginning, find the current amplitude. So let's see. Okay, I remember this one. So we can do, let's see, we're solving for I here, current amplitude, and that would be equal to V over R, voltage over resistance, times e to the negative t divided by RC. But since it's at time equals 0, this exponential is going to equal 1, because 0 plugged in at time 0, so then 0 divided by something is just going to be 0, and then e to the 0 is just 1. So then essentially we're left with V divided by R. We're given both those values, so then we just plug that in. So we have 2.45 divided by 116, which gives us 0.0, let me see here, 0.0212, yada, yada, yada. Just want to go. Okay. 212 or 2112 amps, or we can just say, yeah, we'll just leave it at that, yeah. And that is part J. Part K wants us to find the current at time 3.5 seconds, milliseconds, sorry. So let's see. Okay, so it's just the same thing, but now we're actually plugging in this case, we are now plugging in, instead of t equals 0, 3.5 milliseconds for time, so we have 2.45 divided by 116 times e to the, that's 3.5, so that's milli, so times 10 to the negative third divided by r times, what was it? I think it was r times c. So let's see here. Okay, so we can't do this until we actually solve for c. So I'll just do a little mini little box over here, and I'll do an arrow. So to solve for c, yes, that's why they gave us angular frequency here. So we have angular frequency is equal to 1 over r times c. We're looking for c, a little box again. So rearrange the equation. C equals, it's going to be 1 over the angular frequency times resistance. So we're going to have 1 over omega times resistance. So 5.10 times 10 to the third multiplied by 116. What is that going to give us? So R times C down here, so resistance 116, and then I'll plug this in to find C so that we can use it. 1 divided by gives us 1.69 times 10 to the negative 6. So that goes in our, to solve at 3.5 milliseconds. So then 1.69 negative 6. Ooh, kind of messy here. So then we plug that all into this, so we can solve for it at the specific time. So we have 2.45 divided by 116 times exponential of, and there's a fraction, negative 3.5 times 10 to the negative third times 116, or divided by 116 times the capacitance we just solved for. So 1.69 times 10 to the negative sixth. And that should give us the answer here. So, yep, we were given 3.7 times 10 to the negative 10th. 3.7 times 10 to the negative 10th, sorry. And that is amps. And that is our guy for, which part again? K. All right, part L wants us to find the max voltage across the capacitor, and then part M is just asking for the capacitance, which we already solved. So this, I'll write it out here. So 1.69, because this is part of the solution, negative 6 farads. That is, they kind of did it backwards here. I forgot about that. This is the solution for the last part, but we already had to solve for it in order to get this far. So this is part M. Seems kind of backwards that they asked at the very last question, but that was the last question. And then second and last, which will be our last one, is part L, which asks for the max voltage across a capacitor, so VC. So we're looking for VC. Okay, and so it can be represented by, so looking for this guy, equals voltage times, and then 1 minus E, and then to the negative T over resistance times capacitance. And it wants to know the max, but we are given the problem that the amplitude of resistor and the current in the circuit has its maximum positive value at time equals 0. So again, we're going to plug in t equals 0 here, and we could go and plug in all this again, but as we observed up here, e to the 1, or so sorry, so time equals 0 there, so it's 0 divided by something, that'll give us e to the power of negative 0, or e to the power of 0, which will again equal let's see, yep, we got v times 1 minus 0, and then essentially that's saying the same thing as, so yeah, VC is actually equal to V, since it says at the very beginning it's at its maximum. So therefore our VC is going to equal what they gave us, 2.45 volts, since it says it was at its maximum at the very beginning. And that is part L. And that concludes the last exam for Physics 2.